Yes, hello and welcome to another example here for ORTools. Today we're going to look at example 10, which concerns analysis of variant pairing. So this example 10 you can find online on our ORTools webpage. Example 10 is right here. And yeah, you can just execute this code at home, and this is the code we're going to be going through today. The example here is on child grain pair analysis for lath martensite EBSD map, but the functions have been written quite universal, so you can use them for very different data sets as well. So let's dive right in. We've already done the parent grain reconstruction according to the variant graph approach, and you can look at previous videos to see how that works in detail. So at this point we have the parent EBSD data and the child EBSD data, and we can calculate the variants and plot them. We can also plot packets, we can plot the Bain groups and these kind of things. So this is where we are at in our process. And from line 114 on, we're gonna start this child grain pair analysis. Maybe just wait for this plot to finish. So these are the outlines of the parent grains that we've identified, and the coloring here is the variant identity of each of the child grains, or the child EBSD data, more to say. So this is what we're going to be working forward with, because now we are interested in how is the pairing of these different variants with each other, how does that differ, for example, in the different packets and so forth. So we're going to look into this in detail now. So the first thing we will do is called compute variant grains. This might be a little bit confusing. This is really only necessary if you, for example, have a lath martensitic microstructure where a lot of the variants are just very slightly misoriented from each other. In lath martensite, we have a high pairing tendency between variant 1 and variant 4, which are only a few degrees misoriented from each other. So if we use a normal grain calculation or grain reconstruction algorithm just on an angular threshold, as we usually do in EBSD, we probably won't be able to distinguish those two variants, and we are more looking into the blocks than rather into the variants. But now that we actually have done the parent grain reconstruction, we know the parent orientation of each grain. We know, of course, the child orientation from the EBSD data set. We also know the orientation relationship between the two. So now we can actually look, okay, given those 24 variants, which variant does each EBSD pixel belong to? And then using this information, we can reconstruct the grains again, but based on this variant information rather than on an angular threshold. And this is exactly what compute variant grains does. So we only need to provide the job objects here from the parent grain reconstruction, and we will get returned a new grain object and also a new EBSD object, which we are currently just suppressing here. But you also get, let's say, the EBSD data back with the grain IDs if you want that, as with the normal grain calculation. So we run this, and I must warn you, if it's a bigger data set, this can take a while because it's quite intense computation. But yeah, on this example, it should go rather quickly. So now this new grains object has been computed. We can just have a look. Here we have new grains, 16,763 grains. In this case, it's all alpha prime, so it's all martensitic, all child phase. And this has been a lot more segmented now to a lot of small grains, because we look at the variant detail level. Again, if you don't have a lath martensite microstructure, you probably don't need this step, and you can right away just work with the child grains that you get from normal, from the normal grain reconstruction. So now that we have these grains, we have to actually make sure that we, going forward, when we look at the pairing of different variants, only look at grains from the child phase. And therefore we say new grains equals new grains of job C as the child. In this case, we already only have child phase in the data set, so it doesn't really do anything. But if you have a multi-phase data set, it's important to only provide the grains belong to the child phase to the upcoming functions, which is compute grain pairs. So in this compute grain pairs, we can then actually look at how is the parent tendency of different grains. So there are some standard settings, for example, variance, And if you provide this extra keyword plot, it will also give you the plot, which I think is quite handy, but you can also just go without plotting these things. The results are provided into this out structure, and there you get the results nicely tabulated if you rather want to put them into Excel or any other tabulation software. So we wait for this to finish, and in a minute we should get a very nice plot. So the plot has arrived and it looks somewhat like this. What can we see here? So we have an x-axis and a y-axis, and they both have the labels ID. And in this case, this is of course the variant IDs, variant 1 to 24. And we can now see in this adjacency matrix how high is the relative frequency of the pairing of those variants. So one thing that we can see is that we have those triangles here, right? Like a staircase a little bit, which kind of indicates to us that most of the pairing is happening within packets, right? Because packet 1 would be variant 1 to 6, packet 2 would be 7 to 14, and yeah, since those areas are highly populated, we know that most of the pairing is happening inside of the packets, which is very characteristic of lath martensite. One thing to look at is also that we actually are missing the diagonal here, and that is because by default we don't include the pairing of variant 1 with variant 1, variant 2 with variant 2. If we for some reason want to look at this, we can provide this extra parameter include, and this will actually then also give us the diagonal and take this into account when it looks into the relative frequency. And here we also show an example of providing a different color map. So again, as with other ORTools functions, you can design the plot a little bit based on your personal preferences. So this is the resulting plot, and what can we see? Of course, we again have those triangles here, which are the pairing within the packets. Then we now have a diagonal also as part of our analysis, but we can see it's quite dark, so we have quite low frequency of variant 1 pairing, and so forth. So it's maybe not so useful to include this in this representation, but it's possible if you have a reason to look at this. And also we have a different color map now, as we've chosen by this except parameter color map Viridis. So what else can we do? We can also look at the pairing tendency of packets with each other. I'm not really sure why this would be useful, but it can be done. So just to show you that this is quite universally applicable, this function. So here we have the 4 packets, and we can see that yeah, most of the packets are paired with themselves because we include this diagonal. Of course, we can also just remove this include part, run this again. And then we will see that the pairing tendency has been yeah, changed quite a bit. And the most prominent pairing here is packet 3 with packet 4. So we can also do the same thing for the Bain groups. So these are some of the standard things we've implemented. So for the Bain groups, we again don't include the diagonal, so we can see that the most frequent pairing is Bain group 2 with Bain group 1. And we have very little pairing between 1 and 3. But then again, if we look at the scale, it's probably roughly equal pairing. And I don't think it's actually this useful, this plot. But if you have any reason to look at pairing of Bain groups or packets, this is how to do it. So another thing that we can do is to calculate some other ID. So we can, up to now we've been looking at the packet IDs, the variant IDs, but we can also define our own IDs. And In this example, we're gonna define IDs that are based on this paper here by Morito from 2015 in Matthias Proceedings Today. And in this paper, they look at characteristic block boundaries. So this basically means we look at each of these 4 packets, and within each of those packets we have characteristic boundaries. What we then do is we treat basically variance 1 to 6, variance 7 to 14, and so forth. We treat them equivalently, so we project back all the variants from packet 2, 3, and 4 into packet 1. So we only end up with, let's say, 6 equivalent variants, and then we look at what are the characteristic boundaries between those variants and which one is most prominent. And this is quite important for understanding the mechanical properties of our alloy. So what we do as a first step is therefore we compute this other ID. And maybe if we have a look, new grain's variant ID is just the variant IDs we know, right? We have like a number between 1 and 24 and not a number in cases where there's no EBSD data or parent phase. And this other ID then gives us numbers between 1 and 6. So as you can see by this calculation, this is just projected from all the packets with ID larger than 1 back to packet 1. And now we can actually look into the pairing of those variants, equivalent variants 1 to 6, and see how they behave. So the plot is coming up right here. Yeah, so now we only look at variants 1 to 6. We are missing the diagonal, and we can see that the highest pairing is between 4 and 1, 2 and 5, and 3 and 6. So this seems to be quite characteristic. Now there's also a different way of looking at this. Now that we have those those 6, let's say, groups in our other IDs, so we're not looking at 24 possible IDs anymore, but 6 possible IDs, we can now also start grouping the characteristic boundaries that can be formed between those 6 different equivalent variants. So in this case, we can make groups of equivalent IDs. So we have 4 groups right here, and then we can plot a histogram based on that. So we again look at these other IDs, but we look at are there some of the pairings that are equivalent to each other, and how can we condense this into one plot? So this is how the plot looks, and since these labels are auto-generated, they are quite long. So if you want to use this in a publication, you probably want to manually change these to be a little bit more concise. But what we can see is that we have, mostly variant 1 to variant 4 pairing, and that the pairing between those 2 variants by the misorientation of the grain boundaries is also equivalent to 2,5 and 3,6 pairing. That's also what we saw in histogram earlier. So this is one characteristic grain boundary misorientation that's prominent in our microstructure, and it's way more prominent than the remaining characteristic boundaries. So this is again quite characteristic of lath martensite. Yeah, so you're basically able to define your own other ID and to define your own groups, equivalent groups for your own application. These are some very prominent standard applications. But yeah, you're welcome to come up with your own application here. The function has been designed in a way that can allow general plotting of any types of ID combinations and pairing tendencies. So previously we have implemented a function that also plots those 4 different groups on the grain boundaries, and maybe in the future we will also generalize this function a little bit that it can plot any type of pairing. But for right now it only looks at those 4 different groups that we just had in the histogram, and we can get a nice map of that, which I will show you. Yes, so here we see this map that has just been plotted, so we have different color coding for the different types of boundaries that we find in our microstructure. Okay, the next example is gonna be another example of how to group group certain pairings. So we define a new group IDs here, and those are defined based on those two references here, one from Takayama, one from Bellardi, 2012 and 2014. I'm not sure if these are the first occurrences of this type of plotting, but at least there are some early references with which are quite prominent. So what this does is it looks at the variant pairing. So we again supply this keyword variant, and it defines groups for those variants, right? And those groups take into account which characteristic misorientations there are between variant 1 and other variants. For example, the misorientation between variant 1 and 9 and variant 1 and 19, they are equivalent. So the same misorientation at the grain boundary at the pairing of those two variants. So they're basically merged together into one category within the histogram. Let me just enlarge this. So in this way, we get a quite well-known histogram of the pairing tendency with respect to variant 1. And we can again see that variant 1, variant 4 pairing is most prominent, which is very characteristic of lath martensite. And yeah, that's the histogram. I think it can be quite useful for you to figure out if you're struggling at identifying which microstructure you're looking at, if it's maybe granitic, plate martensitic, lath martensitic. Those histogram will give you quite some characteristic pairing tendencies. Then again, we have this integrated plotting here. If you want to plot the results yourself, down here we have a brief example of how we can do that. It's just if you're not happy with the optics of the plots or you want to customize something, you're also welcome to use this the code that's provided down here to customize your plot a little bit further. In this case, it's mostly the axis, the X tick labels here that have been changed to discard this variant 1 to variant 2, variant 1 to variant 4. So now it's basically only showing the parent, the variant that is paired with V1. Yes, so I hope that this kind of implementation of variant pairing can be useful for your research. I think there's a lot of things that can be done with it, and we intentionally kept in mind to keep this general so that you can define your own IDs. So it could be any other IDs that you're looking at. It doesn't have to be variant packet or Bane IDs. And the grouping, I think, can be quite useful for you as well, to give you some tools at hand to look a little bit deeper into the microstructure that you're analyzing. With that, I wish you happy coding and see you soon.